Hi everyone, I'm Dr. Borgioli from CTS Technical Department. We are introducing a new type of coffee with the chemist. Like many of you, I'm partially in self-isolation waiting for the end of this emergency. And the occasion has presented itself to create a few short videos to explain some materials that are usually presented during the meetings called Coffee with the Chemist we held in our headquarters, and that have now become possible with these powerful tools for you to watch from your residence. I hope you will find them interesting. Luckily, you don't have to bear my big face for long, because I'm going to take the help of a few PowerPoint slides to provide you the relevant information. The data you will see can be sent to you by email on your request. So we start from the definition of nanotechnology. These are new frontiers not developed for our field of restoration, but for other fields, much richer, like the one of the development of PC, then of mobile phones, etc. The new term was coined in 1974, and everything related to nanotechnology refers to the measurement of a specific dimension, that is, nanometer. We use the word nanometer when the dimension is in the range of 10 powered minus 9 meters. That means 1,000th of micron, that is 1,000th of a millimeter. And so we are discussing very small dimension in the range of 1,000,000th of a millimeter. In such small dimension, the surface properties are more important compared to the mass property. I'll give you a very simple example. The force of gravity pushes towards the bottom of a container some solid particles that are suspended. Let's consider a dispersion of a powder pigment in water. We can keep them suspended for a few minutes or maybe more if they are very fine. But at the end of the day, we will see that all the pigment is deposited at the bottom of our water container. This is not going to happen with the nanoparticles that have an interaction based on weaker forces called van der Waals forces. When we have particles that are in the range of tens of nanometers, the forces of gravity don't have the predominance on these forces of van der Waals. If I can disperse and keep in suspension these nanoparticles in a fluid that is not a solvent of the nanoparticles, these will remain suspended indefinitely, and so the force of gravity will not be able, so to speak, to unlock them from the bonds with the water molecules, and in our case, to deposit them at the bottom. In the image you can see some nanocrystals of calcium hydroxide. A nanoparticle material, by definition, must have one of the dimensions inferior to 100 nanometers. If we look at this picture, we can easily see how these hexagonal particles have a diameter greater than 100 nanometers, at least the majority of them. And so they cannot be defined as nanoparticles. Actually, these are special nanoparticles because they have the shape of a tile and their thickness is inferior to 100 nanometers. So we can rightfully call them nanoparticles. I would call this slide the tricky nano because, unfortunately, commercially speaking, nanomaterials are considered the smallest material that we can use. That is to say that nanoparticles have the property of penetrating deep inside the substrate to a level that we cannot reach with other substances. This statement is completely false. The nanoparticles that have dimension between 10 to 100 nanometers are not the smallest material that we can use in the field of restoration. We have in fact molecules that are substantially smaller than 10 nanometers, and molecules like that of water that have a dimension that is effectively atomic. The water molecule is one of the smallest particles in nature we can think of, with 2 atoms of hydrogen which bond with 1 atom of oxygen. The dimension of this molecule is very close to the dimension of the oxygen atom itself. The molecule of ethyl silicate that I represented with the name TEOS, that is tetraethyl orthosilicate, has a dimension close to 1 nanometer. And these molecules are much smaller than a greater part of the nanoparticles. We will see in the future how this makes the difference between the penetration of the ethyl silicate and the penetration of nanosilica. We have then a different field that is the one of small particles, but not so small, in the range of microns, even bigger ones like 10 or 100 microns, thin powders that range in size of a millimeter. This is the field, for example, of the dispersions, like the vinylic dispersions, Vinavil, acrylic dispersions, like Primal, and so on. Some nanotechnologies have arrived in the restoration field, but in a limited number. As nanoparticles, we can mention the nanolime with the name of nanorestore, that is well known. The nanosilica with the name of nanoestel, and other nanoparticles that have been barely commercialized, mainly bound to studies done in association with other consolidants like polymeric consolidants or ethyl silicate and so on. We have nanolayers that are still under study called lamellar silicates. What is a nanolayer? It's a simple layer with a thickness in the range of 100 nanometers or less. We refer to substances that can be associated with polymers to enhance some of their properties. For example, the mechanical resistance, adhesion forces, and so on. In conservation, nanowires and nanotubes have not been used so far. We have a study on the microemulsions that are practically nanopores, that means very small droplets whose size is in the range of less than 100 nanometers, that can work like nanocontainers. The first material to arrive in the market was the nanolime. The idea was developed thanks to the studies of the chemical department of the CSG of the University of Florence, based on the consideration that lime water is a very good consolidant material as concerns the compatibility to consolidate material that has a calcium carbonate as a binder. And so calcite stone, marbles, or wall paintings and valuable plasters. The calcium hydroxide has a limit. Its solubility is approximately 1 gram per liter. And the consequence of this limit is such that many applications of lime water are necessary to add sufficient consolidant material to the substrate. And so, considering that in 1 liter of the solution that we apply on the surface, we have only 1 gram of consolidant, the practical consequence is that usually the lime water has to be applied approximately 20 to 30 times, or sometimes even more. The idea behind the nanolime, the nanorestore, was firstly to increase the quantity of calcium hydroxide on the consolidant solution to be applied, and so to bring it from 1 gram to 5 or 10 or more grams per liter. The second scope was of substituting the water with isopropyl alcohol. In fact, water can be a problem for certain surfaces. Let's imagine that a degraded surface might have, as a cause of its degradation, also great quantities of water due to rising dampness, broken pipes, or damages on the roof, and so on. So, on one hand, the water dissolves the calcium carbonate, and on the other causes issues like the growth of microorganisms. movement of salts, and so on. So using isopropyl alcohol can be a great advantage. First of all, because it is a solvent that will not dissolve the eventual salt on the substrate, and in second place, it works as a bacteriostatic and fungistatic. So it doesn't have the problem of the eventual subsequent growth of microorganisms as it does with water. In 2008, the Nanolime appeared in the market, and after 2 years arrived on the market the Nanosilica, that comes with some limits and some advantages that we are going to examine. Let's start from the limits. First, the minor penetration compared with the ethyl silicate that we will see on the next slides. This is the main limit, but we have to keep in mind other two situations where the use of nanosilicas is not advisable. The presence of salt, and in particularly sodium chloride, that can cause the precipitation of the nanosilicas. As a consequence, all the walls, all the stone elements, the plaster, etc., that are contaminated with sodium chloride, and on coastal area, as this is the norm, must be desalinated before the application of nanosilica. The last point is the high alkalinity. For the stabilization of the nanosilica, there is a small percentage, 0.2% of sodium hydroxide. It is very small, but it brings the pH approximately to 10, and such pH might be too high for certain kind of pigments, and so we do not recommend the use of nanosilica on wall paintings, at least not the indiscriminate one. Let's see the other characteristics. The nanosilica we are going to study the effects, namely nanoester. It is sized between 10 and 20 nanometers, and it is not tile-shaped. It has a spherical shape, so 10-20 nanometers represent the diameter of the sphere itself. It is a water dispersion, and this means the toxicity of the medium, likewise the solvent-based products, is not a concern. The product is not toxic on this regard, and it is clearly not flammable. The absence of alkaline salts in the product makes that no dangerous subproducts will be left behind, like it happens with the alkaline silicates. That is another product on which there would be much to say, but which in this moment we will leave it out. The concentration of silica on nanoester is 300 grams liter. It is very high, and I consider nanoester a concentrated product that must be conveniently diluted. I usually suggest starting with a dilution 1:2, 1 part of nanoester and 2 parts of water. But you can dilute it much more, like 1:4 or 1:5. We consider that from 300 grams liter we can easily dilute the product 1:10, obtaining the quantity of consolidant in the range of 30 grams per liter. So a mild consolidation will happen even diluting the product 1:10. Another very interesting aspect is the setting time of 3-4 days only. This allows us to perform consolidation with silica, that is exactly the same material generated by the reaction of ethyl silicate, but just in 3-4 days. Remember that with the ethyl silicate, the time required for the complete reaction, or at least to reach approximately 95% of the reaction, is 3-4 weeks. And these 3-4 weeks often clash with the timeline of the site. Another important point, and one more reason for using nanoester in extreme situation, is that the product can set with a temperature of 5 degrees Celsius. We know very well that ethyl silicate has a problem of reactivity when the temperature drops to 10 degrees Celsius, where a temperature of at least 10 degrees Celsius is required in the first week, even during the night hours. This poses a limit on certain situations where we cannot use the ethyl silicate. And so the nanosilicas become an excellent alternative to the ethyl silicate when the environment conditions like low temperature or humidity of the substrate advise against the use of ethyl silicate or TEOS. We have therefore an alternative product placed side by side with the ethyl silicate. The last aspect to be mentioned is the possibility of using nanosilica to bond pigments as inert, that is, using the nanosilica like a real binder. You might remember the ethyl silicate was proposed in the past as a binder for pigments and inerts, but its action basically is not that of an adhesive. It is the reaction of a product that can react with some materials, for example sandstone or cacio pesto powder, but its effect on pigments is not always good. A technique which is the so-called stereochromatic scheme that has had some success in 19th century was based on the alkali silicate and non-ethyl silicate binder. We will see this property of the nanosilicas on some slides in the future. So thanks for watching. Remember to like and subscribe, and click on the bell button if you want to receive notification on our next videos.